discussion is going to be on electrical properties of cells. Okay, we should be done here in about 35, 40 minutes, so I'll let you guys, I think, out a little out early today, so the first day. For a cell to do any kind of work, okay, it has to have some way to do the work, okay? And the way it does this is by establishing what we call electrical gradient, okay? That electrical gradient is possible because the membrane has a capacity to have different electrical potential from the outside world and the inside world, okay? The way it initially sets up this gradient is using the sodium-potassium ATP pump, okay? So the initial exchanger, what makes a passive gradient to be created, is the actual sodium-potassium pump pouring a bunch of sodium outside and pulling in a lot of potassium inside the cell. So based on which kind of protein channel I want to open, if I open just a small channel, just allows sodium to come in and it doesn't allow potassium to come out, in essence what I'm doing is I'm pulling sodium inward rapidly into the cell. That rapid change of sodium concentration from inside to the outside changes the electrical potential inside the cell, okay? The normal electrical potential inside the cell is actually negative, okay? So normally everything inside here would be like in a negative vacuum or a negative pressure room, okay? So if I open up the door, air flows in very quickly. It tries to fill in that vacuum, okay? That's what sodium basically does. When you open up the door, sodium pours in and it fills the room up with a positive charge or positive pressure, okay? In the process of doing that, it generates energy, okay? And that energy can be used to do work. That change in potential also can be used to change protein configurations, okay? So I can open doors based on it because they're voltage gated, okay? Which allow other molecules to come out and cause secondary messenger systems to cause different effects, depending on which cell we're talking about, okay? So basically, cells have this ability to use electrical displacement and use that as a resource of energy, okay? So basically, cells are like little batteries. They're able to generate gradients that help moving molecules. They require active transport. Active transport, the most important one is the sodium ATP pump, okay? There's other forms of also ways of establishing gradients, but this is rarely used in cells, which is endocytosis or exocytosis. Most of the time it uses something simple like the sodium-potassium pump. There's different kinds of specialized cells that use electricity specifically. And so when we talk about those areas, you really need to understand the overall function of that cell, okay? And then how does the cell do the work, okay? If we talk about neurons, okay, which is axons, okay, which are trying to displace electricity long distances away, okay? That's what's called energy propagation through electrical conductance, okay? Once the information gets there, it then releases another substance which then causes a receptor binding and have an effect. Now, the other way electrical charge can be used is when it changes the electrical potential inside of a cell. Examples are skeletal muscle or cardiac muscle. When you go from a negative state to a positive state, it allows calcium to be released from inside special storage vesicles inside the cell. Okay? These storage vesicles are, depending on which portion you're calling it, are can be called the sarcoplasmic reticulum, okay? Which is basically a modified endoplasmic reticulum. Okay? Inside these specialized sarcoplasmic reticulum, we have very high concentrations of ionized calcium. The reason we don't have the calcium freely floating inside the cell is it will essentially kill the cell. Okay? So free-floating ionized calcium in the cytoplasm is not a good thing. Extremely dangerous, bad for the cell. So what it does is it only uses that calcium for short bursts of energy, or short burst of doing something, which ends up being changes the configuration of proteins to cause a contraction to take place. Okay? Once the contraction is finished, or wants to be finished, the calcium is rescrubbed and thrown back into the SR. Okay, so the SR is holding the calcium inside its own vesicle, protecting it from the contractile elements. Okay? So anytime that you cannot release stuff out of the sarcovascular reticulum, which means you can't release the calcium into the cytosol, which then acts on the muscle fibers, then you don't get contraction. You need to get that calcium out to get the effect. Okay? And also critical, to stop the contraction, you must pull the calcium back in. Okay? Now, what actually regulates this is charge. That charge is critical for skeletal muscle and cardiac muscle. Just changing the electrical charge from a negative state, which keeps the SR doors are completely voltage gated, regulated, most of them. Okay? So when I let the electrical charge depolarize and the charge becomes positive, then the doors open of the SR, allowing calcium to pour out. Okay? When I repolarize the cell, then those doors close, and the reuptake of calcium occurs very rapidly and pulls it back into the SR. See how that works? Did I lose anybody in that concept? Okay, all right. The other thing that also happens from specialized cells is the electrical pattern arrives when you're looking at, let's say, a neurotransmitter release, say acetylcholine, norepinephrine, anything that's releasing as a vacuole. It's sitting there on a track. Okay? That track is cytoskeleton. Okay? So you have these vesicles literally sitting on like a little roadway that's going to push it out through the membrane. Okay? But that means something's got to be moving that little roadway and pushing it down the rail. The actual push is calcium. The actual molecule that comes in, when the electrical signal comes down, okay, the calcium channel, which is also voltage gated, will open, and extracellular calcium will pour in. I'll show you a picture of it in a minute. Binds to the cytoskeleton, and then pushes the vesicle out into the synaptic cleft, which then affects the neurotransmitter release to bind to the receptor. Okay? I'll show you pictures of that in a minute, so it makes sense. But I just want to sort of get you the concepts first, that these electrical potentials allow different mechanisms to take place, which then can ultimately have the desired effect. Now, depending on what kind of cell you're talking about, there's different degrees of resting membrane potential. If a cell has to do a lot of physical work, lifting, contracting, okay, then it has to have a very, very negative potential because it produces essentially a gradient. The bigger the gradient, the more effective work can be done. And the lesser the gradient, the less effective the actual work can be done. Okay? But there's different things you've got to pay out. If you want to make a cell really negative, it takes what? Time. It takes time. Just think about it. If you've got to pump a bunch of stuff out to make it very negative, like minus 85, it takes time. If I want something that stays only at minus 60, that means the signal can propagate fast. Okay, so nerve cells, which are propagating signals very quickly so you can make calculations and everything, only have a memory potential around minus 60. Okay? Your brain stays that low. Okay? Your heart pacemaker cells also stay around minus 60, minus 65. But your myocardial cells, which are doing a lot of work, they live at minus 85. Okay? So they're going to be able to do the workload of contracting. Skeletal muscle, minus 80 to minus 85. And actually, people have different abilities. Some people have a potential energy of minus 95. Okay? And those people are genetically benefited by that in the sense that they're very strong in lifting. They can lift more than most people. Okay? The downside to them is they're not as fast. Okay? So there is benefits to one way, strength maybe, but coordination and velocity of repolarization may be a detrimental side effect of it. Okay? Now, this difference in charge is between the outside and inside the cell. If they ever ask you that you have micro end potential, in other words, you have a pipette that's in the cell, and both of them are inside the cell, and they ask you what's the charge inside the cell, the answer is 0. 0. Any compartment you're in, based on what's called the Nernst equation. The charge must be 0. Now, if they put the micropipette in the outside and compare it to the inside world, then the inside of most cells is negative. Okay, so it's a differentiation between where you're measuring. I'm comparing this to that. It's not saying what's inside this room. Okay, inside this room, everybody is electrically neutral. There'll be enough positives and there's enough negatives that it will be balanced, and you'll have a 0 potential inside the cell. But in comparison to the outside environment, it's negative in comparison to the outside world. Okay? To do this kind of work, you have to have the sodium-potassium ATP pump. So in other words, if you don't have any ATP production, your cellular membrane potential goes down and eventually leads to cellular death. Okay? And actually, that's one of the things, if you're really interested in what comprises death, is basically all cessation of electrical activity inside the cells. So if you look at somebody's brain for prolonged periods of time, if somebody, let's say, dies, well, you think person dies, they're really not dead for several hours, because electrical activity continues in the brain for several minutes to hours, which could explain to a lot of things if you believe in afterlife or not. I do, but everybody's got their own different philosophies. Some people believe that you hear things or see things because those last cells are firing at the last possible second and gives you recollections and lights and things like that. But that's more of a completely hard knot way of looking at things. But anyways, we'll go on. Potassium is more permeable, so it gets out of the cell, making the interior of the cell to be negative as well. And it changes the resting membrane potential and communicates information, which is what I described to you before. That's what that simple statement was. This is the picture I was showing you. I was talking about the microelectrode. If you put both these microelectrodes in the same point right here, then there'd be no charge, but the differences between this outside world and the inside world is what gives you the charge, which just gives you that negative charge inside the cell. Now, these actual works used to be done with micropipettes, okay? And these are very small glass-filled solutions that have electrolyte neutral solution. And from there, they actually would measure it using an oscilloscope. It's gotten a lot more, of course, complicated than that. And we're actually able to measure electron potential very, very well for cells. And they actually have been studied extensively. Now, this is what it's really hard for most students. They go from a concept, okay, Dr. Nolan explained to me that the cell normally is a negatively charged environment. Okay? Its normal life is around minus 85, let's say, for a skeletal cell or a cardiac cell. Okay? But for the work to be done, I have to change the charge. I have to go from minus 85 to 0. Okay? Because when I do that, I begin to change the actual charge inside the cell, which then causes proteins to change their configuration. So it literally makes them change. Okay? And a lot of the beneficial things of these changes is that they open and allow molecules to transfer across and then have the effect desired. Okay? And I wish the books would say it like that, and they don't. They make it all these complicated concepts. Okay? What we call that depolarization. When you're measuring the change from minus 85 to 0 or plus that, it's considered the depolarization phase. That's the phase that when the cell is going to change inside, that's going to cause an effect. Okay? So if the cell doesn't depolarize, guess what the cell does? It just sits there. Not going to do anything. Okay? If you try to activate a cell, and you would do what's called a micro end potential, just not enough to hit threshold, the cell just sits there and does nothing. Okay? So you got to hit a certain value before you open up these proteins to cause the ions to cross over. Okay? That point that takes place is called the threshold. Okay? Once you exceed that electrical potential as you're coming up and you hit that point, all the channels will begin to open and that cell will fully depolarize. If you don't hit that threshold, it will go back to its normal resting membrane potential and you will get what's called a micro end potential. You might even maintain a certain degree of basal tone by letting some calcium channels open, but not enough significant to cause you to contract. Okay? But it might be very important for cellular discussion or communication to make sure that there's a link between the axon and the cell, but not really causing active contraction to take place. Once the threshold hits, okay, it's an all or none phenomenon. So once you hit it, it's going to go. Okay? If you don't hit it, nothing happens. But once you hit it, you're going to get full effect. Okay? What's going to happen is once you hit the critical value, when we're talking about skeletal muscle and cardiac muscle, we're not talking about pacemaker cells, we're just talking about cardiac muscle or skeletal muscle, you get what's called a fast-acting sodium channel will open. The fast-acting sodium channels, when they open now, will allow sodium to come outside the cell, into the cell very rapidly, causing the voltage from going to minus 85 to plus 0 above. Okay? It's an all or none phenomena. Okay? And what it'll generate is this spike effect. Okay? So you'll see the spiking effect here. So this is your threshold at this point. That's your threshold value. If you don't hit that, then it'll come right back down and it'll go back to its resting memory potential. Once you hit that point, okay, now it fires. This is when all the sodium channels open, and then you're going to get depolarized and you're going to hit the top here. Okay, so this is your sodium channel. Okay, fast sodium channel. Now, once you go beyond that point, we're going to keep it simple initially. Okay? The sodium channels will close after a certain amount of time. Okay, so they don't stay open forever. They stay open for a certain amount of time, which is short, and then it closes. Once the cell depolarizes, the actual sodium channel will close. Now, if it just closes, what would actually do next is the sodium-potassium pump would start kicking in. Okay? And if you just left things alone and you had nothing else left, it would take like this. It would take a long time to repolarize. Okay? So that's not an efficient system. You want somehow to bring it back quickly so you can do it again. So you can do, again, another motion. Okay? You don't want to be sitting there being depolarized, not being able to do anything. Okay? So what repolarizes it is actually very interesting. This time I'm going to open up what's inside the cell, which is in high concentrations. Potassium. Okay? And that makes it very positive inside the cell. But if I open the potassium channels, what happens to potassium? Here's the potassium channel now. The potassium's in high concentration in here. Okay, when I open this guy up, whoops, interesting. When I open the potassium channels, okay, then it pours out. And as it pours out, it takes what? A positive charge with it. And it's going to make inside the cell more negative again. Okay, so that's what repolarizes cells. So if you ever get asked on an exam, what repolarizes cells? It's always potassium. Always. Okay, that's the only one I can tell you that's an always. What activates channels to cause depolarization can be two mechanisms. There's two ions that are found in high concentrations outside the cell. Which are they? Sodium and calcium. Okay? So the two important ones that you're going to have to learn for the first phase of depolarization is either calcium or sodium. If you want a rapid response, like for skeletal muscle and the cardiac myocytes, then use rapid sodium channels. Okay? If you want a more gradual upslope, then you'd use what's called slow calcium channels. Okay? And pacemaker cells use slow calcium channels in their activation. Okay? Again, why is that important? Okay? Pathophysiology next semester. Okay? We're going to talk about antiarrhythmics. Okay? When I talk about antiarrhythmics, I'm not going to make you memorize. I'm going to make you understand. Okay? We're going to take this concept, and I'm going to tell you, okay, if I give a local anesthetic drug, like bupivacaine, which cell is it going to knock out? Is it going to knock out the pacemaker cells, or is it going to knock out the myocardial cells? And what you're going to have to piece together is that bupivacaine is a sodium channel blocker. Okay? So it's going to knock out the myocardial cells, because those are using fast sodium channels versus pacemaker cells are using calcium channels to open up. Okay? This is why we want you to get these concepts so you begin to apply what you're going to be using every day. Next, this is the same picture that I was trying to give you, except now I'm trying to draw it in for you, showing you the fast sodium channels are activated. Please don't think these are not pacemaker cells. Okay, so do not think that, okay, which is I've had people do before, because when you look at pacemaker cells, they look very similar to this. This is an individual nerve that you're looking at. So this is not a pacemaker cell. This is an individual nerve you're looking at. Okay? Remember, what did I tell you about nerves? What do they propagate signals through? At -60. So this is a nerve. Okay? Pacemaker cells are very similar, but the difference is they use slow calcium channels for their first uptake, okay, for this depolarization. So this example is for nerves and for also the myocardial cells and skeletal cells. We'll show you that in the plateau phase here in a minute. Now, one of the things that you have here is that you only have 2 channels. The reason we give you this example is because it's basic. It's simply understanding what happens when you open up a pore. If I open up sodium channels come in quickly, positive charge, cell depolarizes. Okay? Shuts down, repolarization takes place, potassium pours out, brings the charge back to -65, and it neutralizes back to its normal resting membrane state. Okay? That's a simple concept. Everybody get it? Did I lose anybody? Okay, well, okay. All right, now, here's how it's being done at the cellular level. The cellular level, you're looking at the sodium-potassium ATP pump. Okay? That's critical. Okay? That maintains the resting membrane state to a certain extent. But when you see depolarization taking place, which is right here, this sodium channel, okay, will begin to open. Okay? And when it opens, right here, it pours in the sodium, okay, which accounts for this section here. This is this part. Okay? And then that eventually begins to shut down. So this portion eventually closes down completely. And then what allows for repolarization to take place, which is this green phase, is the potassium pouring out of the cell and driving it back into a negative state, which then causes what's called the undershoot. Okay? Because it's going to be basically at that point the potassium channels close, and then everything re-equilibrates back to a resting membrane point. Okay? Now, repolarization has to have 2 things requirement. One is the sodium channels must close. If the sodium channels do not close, then it becomes refractory to repolarization. You have to close the sodium channels before you can actually cause refiring to take place. Okay, what's called an absolute refractory period. Okay, if you have any sodium channels open on the cell membrane, basically you can apply all the electricity you want. That cell will not refire. Okay, so you have to have all the sodium channels closed before you can get that depolarization to take place again. That leaving the sodium channel open is considered an absolutely refractory period. Okay? Once you get beyond that point, if you're still not back to resting membrane potential, okay, and you have all the sodium channels closed, you can now add electrical or some kind of physical activity to cause the thing to refire. Okay? That's called the relative refractory period. So as long as you have enough, okay, you can cause sodium channels to open back up and you get depolarization again. Okay? This will be the Q on T phenomena where you go into VTAC. It'll be something similar to that. Please realize that special cells can use different channels to create energy. This is considered the base model that I just showed you, which is a neural model. Other cells that have specialized and have very unique functions, we're going to talk about neurons, axons, pacemaker cells, myocardial cells, skeletal muscle cells, and smooth muscle cells. We're going to go into every single one of those so you begin to understand that the electrical pattern changes depending on what cell is being involved. The other thing you have to put together in your mind too, that means that the cell membrane is different. It has to be. It has to have different densities of the actual channels that are on the surface of that cell. Okay? Which means that drugs can bind to those receptors or bind to those proteins selectively, causing very different effects in the body. Okay? If I give you a calcium channel blocker, okay, like verapamil, let's say, which has a very good AV node conduction, it will selectively bind more to pacemaker cells, specifically the AV node, and shut down conduction without really affecting contractility very much. You have other kinds of calcium channels that will affect the long-acting calcium channels, which then also affect contractility, which we'll talk about a little later on. So depending on which agent you're talking about, you sort of have to begin to understand that the cells have a certain surface to them, and that surface, which is the proteins, are going to be what ultimately, what pharmacologically you're going to be affecting. Now, axons actually can propagate the nerve signals via sodium channels. Okay? And the reason we teach you this is because local anesthetics are binding to these sodium channels and suppressing it. Okay? And we're going to go into a lot of detail about how local anesthetics work. But you first have to understand the concept of how nerve propagation sends a signal from the nerve body all the way out to the nerve terminal end. Okay? The reason that the cells do this for neurons is that they can propagate the electrical signal very, very rapidly. Okay? So it's a very rapid response. It's also a all or none response. You can get, it's either fires or it doesn't. Okay? And the propagation is by continuous sodium channels being right next to each other in non-myelinated cells. So if you have a non-myelinated axon, you have to have a huge number of sodium channels running right next to each other. As the voltage comes through, the sodium channels open in like a negated fashion, and the electrical signal keeps transporting down. Okay? So you can see it goes from one area to the next, and that means the area behind here has a what? It has an absolute refractory period. So the signal cannot go back. Signal goes only forward, not backwards, which is good because you don't want the signal going back and forth. Okay? Now, so it propagates in one direction and it's very fast. Now, the next concept is if you add something else to it. Okay? Let me come back to it. The other thing you can add to this is you can add a insulator. And it's kind of cool. We do the same thing in electronics. If you go look at your wiring at home, you look at your wiring and it's always covered with plastic, right? What does that plastic do? That's an insulator. Okay? Depending on how good the signal quality you want, you have more insulator on top of it. Okay? If you look at your new TVs and you break the cord, you'll find that a lot of them have a copper inside, okay, or a fiber optic system, okay, and then they have a very big insulator around it. Okay? That insulator protects the signal. The more insulation you add, the better the signal stays. There's less noise that's generated either from the outside environment or the noise that goes out and bounces and comes back. Okay? So that's good. So that's what our cells do too. We use that and we call it as myelin sheaths. Myelin sheaths are just fat that's wrapped around, just like bacon fat, wrapping it around something. So it insulates it and protects it. Okay? And it basically allows electrical activity to go very, very rapidly through that. Okay? But then you've got to ask yourself, well, how does the nerve propagate that? If you're completely covering it with fat, then where are the sodium channels? And the answer is that they're at locations called the nodes of Ranvier. The nodes of Ranvier are areas where you don't have any myelin sheath covering. Okay, they're very small areas, but with very high concentrations of sodium channels. So the signal is generated, sends electrical signal through this myelinated sheath, gets to the next one, fires it, and it goes to the next one. It's called saltatory conduction, because salta means to jump. Okay, so you're jumping from one node of Ranvier to another node of Ranvier. Okay? For our local anesthetics to knock something out completely, so you have no nerve propagation, you've got to hit 3 nodes of Ranvier to knock it out. Okay, so it's volume dependent. And that becomes very important when we talk about this. The other thing important is also is when we talk about local anesthetics is that sodium channels is what we're knocking out. And local anesthetics bind to these sodium channels. Okay? If you can't get the local anesthetic to go into the cell and cause the effect, there's no effect. So if the local anesthetic stays in an ionized fraction, it will not penetrate into the cell. You guys have all seen this. So if you worked in the emergency room or you're taking care of somebody who's ICU doctor is trying to put a central line in somebody who's really acidotic, and the person is complaining of severe pain. Okay, even though he's injected 15 cc's of local, the person's just feeling it like nothing's happening. Because guess what? Nothing is happening. Okay, the local anesthetic is staying outside the cell, never penetrating into the nerve, and has no effect at all. So people that are in renal failure, people that are acidotic because of renal failure or septic shock or any kind of metabolic acidosis, the local anesthetics don't work. Okay, so be cognizant of that as well. Types of tissue is also something that we need to discuss very briefly. There's different forms of tissue. There's epithelial tissue, which are linings. Those tissues can do a lot of work, but they're not going to do active work like contractile force. Okay? Connective tissue, of course, is what holds things together, ligaments, tendons. And then you have your really workload muscles, okay, which are the muscles, skeletal muscle, cardiac muscle. Those are and your smooth muscle are the only muscles really that are able to generate force by causing contraction of the cell. Okay? And we use a sarcomere as that example. And we're going to go into a lot of discussion into the sarcomere. So just understand that this muscle bundle here is actually a bunch of little sarcomeres right here. That's ultimately what we're going to be discussing. That sarcomere is the internal component of what contraction takes place. Okay? And you have to understand how the sarcomere works, and we're going to go into that in a lot of detail. And that's it for today, guys. Any questions?